All right, welcome to our next module. So we have module 2 here, and we're going to be really diving into like what vector and raster data is. So you're going to see this as a bit of a review, but you're also going to see this as more depth of information that you need to know about the two. So our objectives for this is to review the raster and vector data model from module 1, and then we're going to really look at the details of each of those data models. And then we're going to look at both advantages and disadvantages of each of the models. So we're going to start with the vector model because it's the most common one when it comes to mapping, and especially in GIS applications, the vector model is really, really common. So as a review, the vector model stores its data in a series of X and Y coordinates. Sometimes it can have Z, and we'll talk about that a little bit later, but the spatial information is X and Y. And then with that, those X and Y coordinates can be used to create one of 3 basic objects. So you can create points, you can create lines, or you can create polygons. So really, like, we take our vector model, they take that X and Y data, and we can create some sort of form of geographic reality. And so that is like the map trying to portray the real world. And these objects are representing each individual item on the ground, which we call a feature. So individual items or individual things in the real world, like a tree or a bush or maybe a sidewalk or a road, each of those are considered features. Now the features are grouped together. So if I have all my trees together, that's one feature class. If I have all my roads together, that's another feature class. So feature classes are just the grouping of individual features. Then we have attributes, and these attributes give us more information about each individual feature. They're going to give us, it could tell us size, it could tell us shape, it can tell us what type, a classification of some sort, it can tell me color of hair, right? So anything that's an attribute is a describing piece of information. And we take these pieces of information and we store them in a table. The table allows us for easy querying, so it's like, oh, if something in this column says this, then we can find what we're looking for. And then because each feature is linked to a record, that there can only be one and only one record in that data table. Otherwise, we end up with querying issues. Because if we have 2 points at the exact same location that identify the exact same thing, it adds extra information and it takes up memory, and then the computer will get confused when it's trying to find that one feature for you. Also, when you select a feature, the record in the attribute table becomes selected as well. So it's easy to see the link between them. And sometimes in ArcGIS Pro, you can actually get pop-ups. So when you click on a feature, it pops up with all the information from the table, which is really helpful when you're trying to analyze your data. So we call the vector data model a discrete model, which means that it has like starting and stopping points for each of the features. So we have a single point that has a starting and stopping point. It's only one single infinitely small point. Then we can take 2 points and then we can form a line across it. Again, it's discrete, it stops. We can see where the line kind of draws across. If we take a series of these lines and we close them together into some sort of shape, we consider that a polygon. Now it says here, this is where note that it can have a Z value as well, which is, so I can give a 3-dimensional coordinate for each individual point, and then I can have a 3-dimensional line, and I can have a 3-dimensional polygon. So what is key with the vector model is it's considered a georelational model, which really what that means is that the actual information about it is not grouped together as one describing feature. So for example, it says here in the first bullet point that it stores the geometry and the attributes separately. So we have our shape information, which is different from the attributes in the table. But we can link both of them together with something called a feature ID. So when you look at the table, you're going to notice on the left-hand side of the table that there is a ID column. You did not create that, but the computer did. And so with that, what that allows us to do is the computer says, oh, you created this particular feature on the map, and that one matches this row of attributes. So you end up with a random number that, well, it's not random, it's very sequential, but you end up with a different number for every single feature. So if you have 10 trees, you're going to have 10 feature IDs. Then the coverages, shapefiles, and geodatabases have many files that go with it. So for example, shapefiles, it has several files that kind of contribute to becoming a shapefile. And each of those files contain separate information about the feature. So in the case of geometry, you're going to have one file for geometry, and then you'll have a different file for attribute data. But in ArcGIS, you can go in, you can open up the shapefile as one file, because it just comes together as one when you click on it. But if you open it up in Windows, or if you're on Apple, I don't know Apples that well, but if you open those up, and you'll see when you open the folder, it's like a ton of different files. You have like 6, 7, 8 files that go with either coverages, shapefiles, or geodatabases. So each of those individual files that you see in the Windows side actually contain different information for you to use in your map. Then we have composite features that build on simple features to create more complex spatial relationships. This allows us to create maps. So we have like one feature, and it can combine or like be related to another feature, and then eventually I can come up with one single representation of something very complex but easy to understand and easy to read. So we also consider the vector model to be object-based, and that means that each spatial feature has properties that are stored in the same system. So again, notice that it's not the same file. But so when I open up ArcGIS, I can see each of my objects has attributes, it has spatial information, and it can all be combined into one, but it's considered an object. So the objects can be designed, classified, and related to each other very easily. And so that just means I'm taking all of my geometry, and it says topology, my attributes, all that spatial and non-spatial data, and I can create relationships, and I can link them based on those relationships. So for example, if I move something and I know that another feature will move at the same time, I can shift those both at the same time, even though they are in two different areas and perhaps have different attributes. But there's that one characteristic that relates it. So I'm able to do that, and geodatabases allow for that, for that kind of a relationship to be developed. So this isn't really an example, but it is a statement that you have to, that it's good to know. So a field within a feature class table, so whether that be hair color, tree type, whatever it is an object that can have attribute domains attached to it. So a domain, which is specific to the vector model, it is a defined range of values. Now this is really helpful. When you set up an attribute that has domains, then what that does is says, well, you can't have any other type of tree other than these trees. You can only have coniferous or deciduous. You can't have a cactus tree. You can't have some other random thing. You can also go in there and say, you know, I know that every restaurant cannot have any more than, 50 tables because of fire code. So you can say the number of tables at a restaurant should be 0 to 50. And so what that does is it limits the error, the human error of somebody coming and trying to create that data for you and then bringing it back to the computer and saying, oh, there's an error here. So these attribute domains really help limit error, human error, when we're trying to work through our data. So kind of moving on from the domain idea, which is like really handy to help out with data collection, the only models One of the key things about the vector model is that it only models those parts of the features that exist. So if I don't have a certain data of my vector, like for that particular feature, then it's not going to be able to show it. And if I, for example, I'm trying to capture a very particular shape, if I can't see it, it doesn't really exist. If I don't have it collected, and we're in data capture 1 here, if I haven't captured that information, I can't show it. So what's nice with the vector model, as well as kind of another feature, random feature, is that no representation of the background is required. So that means I don't need extra data. I just need my points, my lines, and my polygons, and that's it. I don't need anything in the back. So therefore, we actually improve on data storage, so we don't need to use up quite as much space. And then also, a length of a line is dependent on the length of the real world object, right? So that's what we call scale. So if we have our scale set, we know that the length of that line is going to be based on the scale of the map, and therefore there's a direct relationship to reality. So we can also make a note that vector models have high positional accuracy when everything is done correctly, right? So it says you can have one element have very high positional accuracy, but it's independent of the rest of them. So one point can be more accurate than others. So in the world of land surveying, which is kind of what my background is in geomatics, that I can have one point that is really accurate, and then I can have other points that are not so accurate in position. And because it's based on the equipment that I'm using, it could be based on the control I have in the field, it could be the actual user of it. And this still has that ability for us to have that flexibility to show that data. And so with that, like I aim to have the same positional accuracy, but you don't need to create a network and adjust an entire network for every feature that you have on your map, which is really a great benefit. Then there is the structure for storing attributes as well, and because we can have multiple values, we can have many attributes and multiple values for those attributes. Just be careful though that if you are going with many values for one attribute, it might be easier just to create an extra column and then just have some categories that have, or sorry, some of the features to just have it empty and there's no data there because it doesn't need to have multiple values. So a benefit of the vector model is that it supports advanced data analysis and relationships. So like I was saying, for example, if I have a tree and I notice that I have a hill and there's a certain kind of tree that grows on that hill, that I could take a look at soil, I could take a look at the other vegetation around it, I can look at human access, I can look at infrastructure. There's a lot of different types of analysis I can do to try to determine why is it that one tree that is there. Then we also can say with the vector model, again, these are kind of random points put together and just thoughts of what the vector model is, but we can combine different layers to create an output. So we can really take a lot of advanced information. Like I was saying with the tree, I can look at the slopes, I can look at what direction the hill is pointing, I can look at infrastructure, all of that. Each of those are considered different layers, and then I can get an output as to what I need to know and how I need to define that answer. So with all of that, let's talk about the advantages of vector models. So data is stored at the actual positional accuracy. So when I go out and I collect data, if I have poor accuracy, the data that I collected is going to show up in a poorly accurate position. So that data capture is really important for the vector model. when we talk about precision, the precision can be very high. So if I go out and I'm collecting trees, I can know them precisely where they are. It may not be accurately, because the accuracy is going to depend on many other things. So, but I know that every time I go out and collect that tree, and I put it into again, I try to show, oh, has it changed, or is there any new information about it? Maybe it's gone. I know that that location is relatively precise, so on the map, so I can relate it there. Then there's the storage of numerous attributes. So that is a great benefit of the vector model. So if I'm trying to do some sort of classification of data, if I can find multiple attributes of a single item, it makes it easier for me to classify very complex data and come up with a much better solution. There's also the flexibility for cartographic display. So there's many, many ways to show vector models. And so we have all kinds of symbols for it and all kinds of patterns and textures and everything. So there's a lot of flexibility, which is a big advantage. Another slide on their advantages, it's compact, right? So we mentioned that before, that it doesn't require as much information because I don't need a background. I can also come up with really advanced relationships and supporting those relationships, and that's known as topology. And so we're not going to have, like, for example, two polygons overlapping each other when they're not actually overlapping each other. So it will pick up on that and be able to fix up. You have to set that, by the way. It doesn't just automatically do that, but it is something that you can do. Then we also, another advantage of it is it's really good for certain types of analysis, especially looking at areas, lengths, and networks. Because I know where all the corners are of my polygons, because I know exactly where the road is, I can have really good analysis as to, for example, distances, or perhaps trying to find the optimal area for a business or something. But with every advantage, there's always some sort of disadvantage that comes with it. So with the disadvantages for the vector model, the topological structure is really intensive. So if you have a lot of data and you're trying to put it all together into one map with many layers, it becomes really, really intensive, and it takes up a lot of processing time. And you really need to spend a lot of time cleaning the data. So when I say I'm cleaning the data, what I mean is that I'm trying to remove any blunders or big errors. I'm trying to improve the accuracy. I'm trying to make sure that there's no duplicates of data, that everything is in the same coordinate system, all of that. So it does become very human dependent to be able to do that. Also, we have very complex algorithms. So in order to get the data together, you're going to see, for example, with the network assignment that we do, it's really complex. So what we do is barely scratch the surface, but there's so much more that needs to be added to it, and just to make it even further with the information that we want to work with. And then finally, the continuous data are not effectively represented, which means, for example, if I'm looking at temperatures, temperature doesn't just stop, right? That's discrete. The vector model is a discrete model, which means that an item will just stop. So for example, a tree, it stops. Like there's an end of that tree. There's an end of a building. There's an end of a road. But with continuous data, that doesn't happen. So you really can't represent that using the vector model. So again, it's because it's really well suited for some analyses, it's really not suited for other analyses. So for example, if I'm trying to look at multiple layers and I'm trying to overlay them and apply it like a mathematical analysis, it's not great for that. So usually we'd go to a raster model for that. And then because it has a more complex data structure, even though you think, oh, well, it's just points, lines, and areas, but nothing is regular. Everything's kind of placed around. There's no rhythm or like pattern to it. So it becomes a lot more a lot more complex, and then you add like topology to it, you add relational properties to it. There's so much that goes to it. And then because of that, you need to do more maintenance. So looking at that again, going back to it and keeping it up to date. And if you change one thing, you've probably got to change 20 others. So it is quite complex to work with. So I want you to take a moment to do this on your own before you continue on. So it says, describe 5 real-world data representations that would be suited to using the vector model. So if you want to pause here, I will, and then write them down, and then we can they come back, and you can see kind of what I'm going to say. All right, welcome back. And so let's talk about some 5 real-world data representations. I've given so many of them throughout this lecture, so I'm just going to name a few. So trees is a great one. The land parcels, so like where your house is on, there's a property boundaries and everything. That is a really good vector model. Road maps, for example, those are all vector models. And then trying to do an analysis as to where to build the next hospital would be another really good real-world data representation. And so looking at, for example, demographics specifically for that. And then another one would be for navigation routes. So sending shipping containers across the world. So that would provide specific routes and very discrete information. All right, so now the last half of today is looking at the raster model. So the rasters are, as we mentioned last time, they're cells in a grid, and they kind of represent point features for each grid because it's kind of one item in each cell. So each cell value, or we can call it a pixel, has one aspect of reality. So we can only maintain one piece of information for every pixel. Then it has a small squared unit of area. So each little box is one squared unit with one value. And so if we take the size of that little pixel, we can have very relative measure, like a very relative measure of small and large, right? So we have a small cell, which will give us a high spatial resolution. Or we can have a large cell, which gives us a very low spatial resolution. So we have some examples coming up here, but not this slide, of course, but it's coming. So with that, the feature representation is very dependent on that pixel size. So this is known as spatial resolution, where if we want to show a tree, but we have a 30 meter by 30 meter pixel, which is the classic for Landsat data, which is a satellite, then I'm not really going to see the tree. I'm going to see maybe a group of trees that are in there, but I won't see an individual tree. So the feature representation is very, very dependent on that. And then the entire area of your map is represented by pixels. So background, foreground, all of that is represented in pixels. This is where continuous data is really the best represented. So for example, temperature or precipitation, elevation is another really good one, because elevation doesn't just stop. It exists throughout. And what is really great about the raster model is it's simple. So it does speed up the analysis. And so if you're running an analysis with raster, you're going to find that it's actually faster than going through a vector model. And the complexity of some of the ones that the raster model can do is actually simplified greatly if you use raster versus a vector. So every pixel can store a value, and one of them could either be an alphanumeric or numeric. It would generally say numeric, because we usually use it to represent some sort of mathematical value. And again, it only has one value. High resolution, if we want to go with spatial resolution, comes at a cost. So if we have smaller cells, we have to go with a greater information storage. So again, if you want to improve your spatial resolution, just like a camera, right? If you think back to like the older cameras, if you had a higher spatial resolution, with your camera, it was more expensive. And so that's still the same thing here. So if we want a higher resolution, it's going to cost us. It's going to take up more storage space. Also, if we're trying to generalize, well, and I mean the whole thing is generalization, it's going to have this blocky feature experience. So, try to see a particular object, like the edge of something, it's going to be kind of pixelated. So when I say bloxy, it looks pixelated. I often like to use the example of like the original Super Mario Brothers. It was all kind of pixely and everything was like at certain angles because that's how the pixels were set up. So there are 4 main elements in a raster model. And so we have the cell value, we have the cell size, we have something called raster bands, and we have the spatial reference itself. So I'm going to go through each of these as we move through here and then just to kind of explain them a little bit more. So the cell value is the value that the raster pixel has. And it has one particular phenomenon that is trying to show at that location, and we can identify it based on rows and columns. So it's showing here 2 different ways of trying to identify this. We have something called an image space, which means that 0, 0 is up at the corner right here, and then we would count the columns this way, and then we'd count the rows this way, right? So we count 1, 2, 3, 4, 5, 6, 7, 8. There's 8 rows, and then 8 columns as well. So we can identify, for example, this pixel here. I can say it's 1, 2, 3, 4, 5. That's 5 columns over, 1, 2, 3 rows over. So that would be at row 3, column 5. We also have the coordinate space, which is like the real world coordinate, and depending on the map projection, this 0 can be somewhere else, but it's going to be placed in some sort of grid location on the Earth, and we can actually like spatially reference that. But based on the cell value, notice that I've just talked about the coordinates of the value, but over here I have cell values that I can actually identify. So here it's saying it's 1, here in the blue it's 2, these light yellows are 3. 5 is green, 4 is teal, 6 is kind of like a yellowy green color. So it has 1 value, and that's it. And I can identify, for example, this 5, like I said, was in column 5 and row 3. The value itself can only be an integer or a floating point in this case, but so that means the floating point means it's decimals. An integer means a whole number, positive or negative. You can have the alphanumeric as well, but we'll just stick with numeric for this. The second type of element that is important with raster models is cell size. So you can see here, if we have a shape, this polygon, and it's on the ground, and then we want to try to figure out a resolution that we need to use to be able to represent it. So if we use a 1 meter cell, that means each side of the cell is 1 meter by 1 meter. We can put the shape in the background here, and we'll see which pixels are actually colored in based on that shape. If we switch to 2 meters, we can see what happens to the pixels that are filled in compared to this one. And then if we go to 4 meters, you can see really what happens there. So as we decrease the spatial resolution or decrease the resolution of these cells, we're going to see a change in the cell size on the ground. We're going to see the change with higher resolution, or with the resolution, that's what we're doing. You're going to see the spatial accuracy decrease as you get into larger pixels. You're going to have faster display if it's larger. And you're going to have faster processing because there's fewer cells usually for this. I want to call it coarse because we use the word coarse in remote sensing for the lower resolution or larger pixel size. And also the larger pixel size reduces the file size as well, so we don't need as much memory. Then we have the raster bands, which is the third element of rasters, and this is really the power of rasters. So we end up with these pixels with 1 value, but we can take multiple layers of rasters and put them together to create something very complex and very easy to understand as we view it. So we can have one band, which one band would be one layer, or we can have multiple bands, which means we have multiple layers. Now, in remote sensing, we use the electromagnetic spectrum, and we can identify certain regions on the electromagnetic spectrum. That is why it's called a band. It's an electromagnetic band that we use, or bandwidth is the width of that band. That's in remote sensing though, but you can also use, you don't have to use images to do rasters. You can take any information and create it into a raster, and then use that and use different layers to process. So it doesn't have to be like in the electromagnetic spectrum. But what we do is we use all these bands, and we can identify certain types of features. We can have classifications. We can do all kinds of fun stuff with it. But it keeps all the different data separate into different layers, and then we call those bands. Then the last of the elements for the raster model is the spatial reference. So I mentioned that we can georeference this, and so we have to do that in order for it to actually align somewhere on the Earth, and so that we can put other data with it. So it has to have some sort of spatial reference, and in this case, for example, it shows the cell centers, and it's each of those centers that is aligned with something on the Earth's surface. So what's really key is with, especially like for example, elevation, we can have all kinds of errors that come with that because we have Earth curvature, we have, just the elevation itself causes like spatial error. There's a lot of things that come out of that. So what we have to do is be able to like warp it a little bit to put it onto that Earth's surface so that it actually fits properly and is showing what it's supposed to in the right location. So we can do that very easily with rasters, and it's using cell centers. And sometimes it's using the corners, but you can usually use the cell centers for that. So here's an example going back to the spatial resolution and difference in what you're going to be viewing. So we can see a cell size of 15 meters here, and then a cell size of like 15 centimeters, 15.24 centimeters here. So we can really see a big difference between the two. We can pretty much, at 15 centimeters for cell size, we pretty much can see your car driving down the road very easily, right? Not real time, but in a static photo. So but here you can't see that at all. So there's a big difference between those, but this is a little bit easier to generalize where this is so detailed that I might end up with errors because it's all with such noisy, with such high resolution. Here's another couple examples. So slope and aspect are two different things that we use to show elevation. And so slope is exactly that. It gives you a color based on the slope value, so how steep it is. Aspect is what direction that slope is facing. So that's the cardinal direction. So northeast, southwest, or northeast, southeast, southwest, or northwest. Then we have hillshade. Hillshade is also really interesting because it colors it in, like it shades it based on like a sun being projected onto it. And so you can see that some areas are going to be brighter than others, and that will impact how it looks. It looks like the sun shining on some sort of hill, so one side will be bright, the other side will be dark. So rasters, there's a lot of different kinds of rasters. Some of the more common ones are listed here. So we have satellite imagery. There's also digital elevation models. And again, digital elevation models and digital terrain models, one can argue whether it's if they are going to be rasters or not, because if you get LiDAR is kind of a funny one because it is kind of both vector and raster at the same time, showing elevation. But we like to show elevation as a raster because it is continuous data. There's also orthophotos and land cover data, so that's like forests and prairies, etc. We can have bi-level scanned files, digital raster graphics files, and then GIS software specific raster data. So if I'm going to create some sort of GIS raster, then I have my own special type for that one. So again, I'm going to give you guys a couple minutes, and just not on here, but I'll give you a couple minutes to come up with your answers for this. So, and again, I've given away quite a few. Describe 5 real-world data representations that would be suited for using a raster model. So I'll give you, you can pause here, and then you can see how it matches with me. All right, so some of the 5 that you can think of, precipitation can be one. Elevation, temperature, those are all different types of continuous data. I could be looking at permafrost and how it deforms over time. I can look at sea ice coverage, that's another one. And so those are 5 examples, but I could go on and on and on and on, because anything that you can use an image for you can use the raster model for. So in summary, vector data is a simple structure to develop. You can use overlays, and you can see through each of the overlays, which is helpful. And you use it for discrete modeling, discrete modeling. Rasters are larger and they require more space. And they're a little bit more of a complex data structure because it's a whole bunch of cells stuck together. But the raster size and the cell value, the cell size and the cell value can determine the precision of the data, but it also determines what you can see. And rasters are ideal for mapping continuous data. So that is the theory that you need to know for this particular objective. So I'd like you to go into your Mastering ArcGIS Pro book and make sure you read Managing Vector and Managing Raster Data. There's no exercises, but you'll need to complete assignment 1 because this includes all that information. And there's the references from today. And thank you very much for joining me, and I will be back with objective 2.